morning, everyone. Welcome to this session, doctoral meeting session on our Space Science and Technology PhD program. I would like to thank you all, our 7 speakers today, and all the audience, including the supervisors, for being here. Today, we're going to be discussing, talking, and listening to the presentation of the PhD students that are working on different problems related to astrodynamics, space tethers, also space debris, GNC problems related to space, etc. Right, so it's quite interesting topic. We have also some industrial PhD thesis, some academic PhD thesis, and I hope you all enjoy. Okay, so sorry for these minutes of delay and these problems with the connections, but I think we are all here now. We're gonna start with Luca and Sadaf. They're gonna be presenting topics on space tethers, right? And then we will continue with Sergio and with the other established before. Okay.
So, good morning. Thank you everyone for being here. I don't know if you're able to see my screen.
Yep. Yeah. And your pointer. Yeah.
Okay. Thank you. So today I'm going to talk about this my PhD thesis, which is on the topic of automatic maneuver detection via, well, basically based on statistical methods. And this combined work means that we're trying to use heuristical and optimal control methods, basically. And well, this thesis is funded, well, we're in contact with some projects of GMB and also some networking partnering initiative from ESA. Actually, the co-director of this thesis is from ESA. So, well, if you want, we can continue. First of all, sorry. So, as you already know, the Earth's orbital congestion is increasing as we keep launching more and more spacecraft. And the thing is that the number of space objects has increased up to a point that actually current missions are being affected by the size of the orbital population. And here we have a typical plot of the growth of the Earth orbital population by object type in this case, and we can see these two peaks, which are due to China's anti-satellite test and the Syrian Cosmos collision that I think we are all already aware of. But the thing is that most of these objects are due to satellite breakups and collisions. So the thing is that we need to monitor the space. We need to monitor the space and catalog the objects so we can predict their state, and we can avoid future collisions, and we can actually plan the future space missions in a safer way. So for this, we typically use radars, and with these radars, we are able to determine the entire state of objects up to a certain accuracy. But the thing is that we can only do this for objects that are close to us, like in LEO or even MEO, like low Earth orbit or medium Earth orbit. But if we go beyond that, we need to use optical telescopes. So that we only gather optical observations, which are partial. And the thing is that today I will talk about optical telescopes and optical observations. So, we'll focus on maneuvers of basically MEO and actually geostationary objects. Okay, so I will show you what is the typical survey scenario for optical observations. So in this case, we have 2 ground stations. And this white dot would be our spacecraft that actually we can see as a white dot, more or less. So we can measure, we can measure 2 angles, typically, the right ascension and the declination. But the thing is that we're missing the distance between the ground station and the object. So we don't actually know the entire state of the object that we are observing. So this creates a need to have a good a refined model for the dynamics of this object. And well, for higher orbits, this is simple. The only things that you really need to tune is, for example, the reflectivity coefficient, so how the solar radiation pressure acts on the spacecraft, but giving you know that more or less accurately, you can estimate the orbit. And for example, if you retrieve observations that you typically gather once or twice per day, you can associate observations with objects. So this is typically solved. Still, we have some issues when there are objects that are really close to one another. But the thing is that more or less we're working this way. So space surveillance activities are actually have solved this problem. But this problem, let us go into the state space filtering, so sort of a mathematical formulation for a problem. So in the end, we have a stochastic system in which we have the state of an object, which follows some sort of it follows some dynamics, some dynamical model, and then we also have some measurement noise, which some dynamical noise that we are not able to let's say to know, and this would be some kind of Wiener process that we are not able to model, and this would be, for example, accelerations that we are not able to catch, or some things that we are not able to model in general. And we also have some measurements here, CK, and we have some measurement model for, so given a state, we can create it's compliant, so the observations comply with some state, but we also have some noise for the measurements that actually are given by the measurement noise of the telescopes in this case. So well, based on this, we have a probability distribution function, as you know, which is typical for stochastic systems. So we have a probability distribution function for the state, which may be at time zero. We have so let's say we know where the spacecraft is with this accuracy, and then we propagate it to a future time. So well, actually, this PDF is programmed. So we have so the expected position is we really don't know much about the position, let's say. So there's a dilution probability. So whenever then we try to include the information coming from the measurement, and when we combine both, we have a posterior probability distribution function that is conditioned on the measurement sequence, so we can have a best estimate of the state of our observed object. So in this case, well, this is what you really do when you do some state space filtering. But the thing is that, well, actually, yeah, you determine the probability distribution function. Because, for example, for collision avoidance, you may need to also consider some sort of covariance in order to compute collision risk analysis and this kind of stuff. So the thing is that actually the physics are not deterministic, let's say. So now we will move into the maneuver case. So up to now we have only considered the typical ballistic motion in which the satellite simply orbits, and you consider perturbations and all this, and also you consider noise from the model and from the observations. But the thing is that if you have a maneuver, as you can see here, then the state of the spacecraft changes dramatically. And for example, in GEO we have times that are sometimes 1 day or even 2 or 3 days. So the thing is that if you don't see the object for 2 days, then the state of the object might change dramatically. Or even you may be able to observe the object, but the thing is that since you don't have information regarding the range, you may oversee the maneuver. So because, well, look at this telescope on the left. In this case, we may assume this is due to the measurement error, so that we are not able to detect the maneuver, and this actually is a real threat. So the thing is that we in the first. So what we're going to do is we want to characterize this in terms of some control distance metrics that tell us whether we are able to, so whether some spacecraft has maneuver or not, based on, so we want to make decisions based on a control distance metric, let's say. And we want to do this in a statistical sense. So if we go for the mathematical formulation of this new system that is able to maneuver, what we have is a stochastic hybrid system. This is our proposal. So we have a state But we also have a model. This model is, so the system is augmented with this model, which is indicated by M, which is the mode active at a given time interval. In this case, so this mode will indicate if there have been a maneuver or not. And well, this also, we could consider this as different types of maneuvers. For example, well, it depends on station keeping or collision avoidance, but for this, let us just use this as an indicator functions that tell us whether there has been a maneuver or not. Okay. So the thing is that, well, again, we start with some PDF of this state. Okay, and then when we propagate, if we include the information regarding the maneuvering model, then we have a multimodal distribution. So, for example, this distribution on the right would be the ballistic motion, so no maneuver, and then on the left this would be some sort of maneuver. And then whenever we have an observation, we can apply this control distance metric that we have already mentioned, and then we can guess which is the most likely mode that was active in the previous time step. And in the end, we can still combine information, so that we have a PDF for both the state and the active mode. Actually, we are detecting the maneuver and characterizing it in an automated fashion. So, well, this is basically the goal that we're trying to achieve. And how are we going to do this? The first thing is to use, to define this control distance metric. So in the literature, actually the state of the art is to solve a nonlinear, like a direct optimal control problem, in which you assume the thrust is continuous, and you minimize the distance to the observation, or just an orbit, depending if you want to use the observation as its partial nature. So you don't have information about the range, and then you combine this with the cost, with the fuel consumption. But the thing is that this, I mean, you can do this, but the thing is that solving this problem is quite expensive. If you want to do it, for example, if you want to do it a lot of times, you will need to if you use statistical methods. For example, some sort of sampling methods. So what we propose to do is to use a simplified approach in which we still need to solve an optimization problem, but just over two variables. So we take advantage of the Gauss planetary equations, and we assume they are unperturbed. So we have, and we linearize these Gauss planetary equations at the impulsive parts, which are applied at fixed true longitude values. So in the end, you just plug in two values for the true longitude that are, so you need to model two different bars so that you can transfer between two arbitrary orbits. Otherwise, if you just perform one bar, you cannot go to an arbitrary state. And then you plug the true longitudes at which these two bars are performed, and then you only just need to solve this. You need to inverse these metrics, and you get the information regarding the control cost. This is a simplified approach, but the thing is that the results are quite in line with the ones given by solving the direct optimal control problem. So this is just a simple metric that is faster to compute. So what we do is, we use this control metric. In fact, we can use either both of them, but the thing, and then we apply some, so we define some allowable bounds and this sort of admissible region. So for example, this plot on the left is how the range, and in this case the range rate, so the variables that we are not able to know, we define, so these are the unknown variables, the unobserved ones, so that we can build a map of the control cost required to reach the change in this range and range rate values, let's say. So we define an admissible region for this. So we can assume this admissible region is a sort of probability distribution function based on the fact that we expect maneuvers to be fuel optimal, because operators are typically want to optimize fuel consumption to extend the lifetime of their satellites. So we can, so first of all we build this probability distribution function, and we we can use this to filter out the sequence of observations, as I will show in a moment. So going back to how we can use this information, so imagine we have a sequential filtering. This is the sequential filtering scenario, and we have an initial orbit. Then imagine that a maneuver has occurred, so we have an observation, a measurement, let's say. And then our admissible control region, let's say our admissible region would be this dashed line. And then the intersection of the admissible region with the measurement, which is what I've shown in the previous control plot, is this red potato here. And then, well, we define and we say, well, this is more or less where the spacecraft would be at this point, if we assume a maneuver has occurred. Then, as new observations come in, we can filter out. So this region is reduced, so that we get more, like, in this case let's say if this would be the PDF would be in this case multimodal, but the entire volume would be smaller. And at some point, we will be able to locate the spacecraft, let's say. So the true hypothesis in this case would be this one. So there will be a maneuver that we have correctly identified based on the admissible control region. So basically this is our proposal. And for this, we need to do we need to compute this. So we need numerical methods to apply this multiple hypothesis testing. And for this, we basically use sequential Monte Carlo or particle filters, in which first of all, we sample from, let's say, an initial distribution, which in this case would be, the initial PDF. So we get a sample distribution, and then we propagate the distribution according to this dynamics, in which we can include all the stochastic terms like process noise or whatever. And then we sample from the admissible region, well, actually from the overlap between the admissible region that we consider and the measurement. And then we can propagate forward in time until we get some hypothesis that has been shown to coincide with the measurement sequence. And that's how we actually perform the sequential filtering based on this. And well,
Guillermo, you have already consumed 10 minutes. Please.
10 minutes. Okay, there's just a couple of actually two slides more. Thank you. So well, basically what we do is we sample from this admissible region using, in this case, we use Markov chain Monte Carlo methods that are typically used to explore probability distribution functions. But we can also characterize maneuvers, and we can also sample based on maneuvers that have already occurred, which is actually in a sense, this has already been done in these two works that I'm citing here. And these works, and we're actually trying to fuse both the optimal control methods and heuristic methods into a single formulation. This has some statistical sense in the form of a stochastic hybrid system, which, well, is thought to improve actually it does so in an automated fashion, and it's thought to improve the performance of the maneuver detection and characterization, and also the space surveillance and tracking filters. So basically, well, we've already presented some work here on the 8th European Conference on Space Debris, which was held in April this year. And we are also planning to, well, actually, before summer, we're preparing to submit some paper to the Advances in Space Research journal. And well, basically, we have been shown to be able to track maneuvering targets using optical observations. And well, these are some results that we have obtained for real data. I don't want to clutter you with this because there's a lot of information that I need to provide in order for you to properly understand this. But the thing is that we have successfully applied this to real measurement data, and the residuals are in line with what which is expected to be in a real operation scenario. So our future work would be to adapt the method to radar observations for LEO objects that are actually well, it's quite a challenging task because there are a lot of objects that are really close to one another. So probably the admissible region concept might not be very accurate, and well, may lead to some problems there. And well, also we need to compare against the state-of-the-art methodologies in terms of, and also the industry approach in terms of maneuver detection and characterization, which is not, there's not much information about it. That's why we've not yet performed this comparison, but still we need to compare against the former work. And basically with this, I'm done. So thank you for being here. I'm ready to answer any questions you may have.